Picture this for a second. You're lounging on a deck chair by the ocean, watching the waves wash over the sand with seagulls soaring carefree in the sky. For you, it's the perfect vacation snapshot. But for the pilot of an airliner climbing into the sky above that very same airport, those same birds are one of nature's most unpredictable and dangerous forces. A bird striking a plane, or a bird strike, seems like an unlikely scenario until it happens. But in the world of aviation, it occurs thousands of times a year. And the most critical scenario is when a bird doesn't hit the sturdy cockpit windshield, but goes straight into the heart of the aircraft, its jet engine. What truly happens at that moment inside this multi-million-dollar engineering marvel? Does it turn into a pile of scrap metal, or is the technology built to withstand such an impact? Today, we're not just going to break down this scenario theoretically. We're going to look deep inside the turbine to understand the battle that unfolds between thrust and a living mass. You'll discover the ingestion mechanism, what happens to the bird and the engine during a high-speed collision, the real consequences from a simple dent to a complete loss of thrust, and the heroic emergency landings you later see on the news, and most importantly, the prevention measures, from high-tech repellents to kamikaze falcons. This is the story of how fragile life challenges a titan of engineering, and why, despite its apparent vulnerability, modern air travel remains the safest mode of transportation. Fasten your seatbelts, we're beginning.
Let's be straight. The picture of a bird versus airplane seems like an unfair fight. So what if a kilogram of feathers and bones hits tens of tons of aluminum and titanium? But here's the paradox. In this clash, it's the bird that turns into a destructive projectile. Why? It all comes down to the physics that plays out at the engine's inlet in a split second. Put yourself in the bird's place. You're soaring in the sky, and suddenly an iron mountain with a roaring hole in the front is rushing toward you. This isn't just an opening, it's a turbofan engine, a giant vacuum cleaner sucking in tons of air every second. Your flight speed and the plane's speed are combined. Now add the compressor blades spinning at several thousand revolutions per minute. Meeting them is like being thrown into a rotating blade weighing several tons. Now the view from the pilot's cockpit. You hear a dull thud. Bam! This isn't just a simple bang. At that moment, a 1-kilogram bird flying toward you at 300 kilometers per hour gains kinetic energy comparable to a cannon shot. Its body, consisting mostly of water, behaves almost like a fluid under monstrous pressure. It doesn't just get sliced apart, it explodes, delivering a shock wave to the first, most vulnerable fan blades. And that's when the chain reaction begins. The first blow hits the thin titanium fan blades. They bend and shatter. The debris from the bird and the blades themselves fly deeper into the engine's working guts, the high-pressure compressor. Imbalance. The engine's rotating parts are now unbalanced. A tremendous vibration occurs, which the pilot feels throughout their entire body. An avalanche of problems. The damaged blades can no longer compress air efficiently. Thrust drops. Fuel flow can be disrupted, or spilled oil can ignite. So what, you might say? One hit and that's it? Modern engines are real fighters. They're designed with this kind of surprise in mind. Before making it onto an airplane's wing, every engine undergoes brutal certification tests. It's run at full takeoff power and shot with birds from a special pneumatic cannon. The main criterion for success is this: the engine must survive. It may shake, smoke, and operate with reduced power, but it must not disintegrate or detach from the pylon. The design is built to absorb the impact and contain all the damage within its strong casing. But there's a nuance that changes everything. One bird is an unpleasant incident, but a flock, that's a catastrophe scenario. Imagine several such projectiles entering the engine one after another. The chances of it weathering such an attack plummet. And if birds hit both engines at once, it is precisely this risk that forces aviation engineers and airport services to treat birds with such serious respect. the "we have a problem, but we'll handle it" scenario. This is the failure of one engine. Modern aircraft are designed to safely complete takeoff and flight on the remaining engine. For the crew, this means immediately declaring an emergency and working through a pre-memorized checklist. Stabilize the aircraft, reduce thrust on the damaged engine, possibly shut it down, and ensure fire safety. After that, it's an emergency return to the departure airport or a landing at the nearest suitable airfield. This is a complex but routine situation for trained pilots. The fight for every second scenario. This is the failure of both engines, an extremely rare but critically dangerous scenario, especially at low altitude during takeoff. The plane turns into a heavy glider. The crew's task is to instantly find a place to land and attempt to restart the engines in the air, if altitude and speed allow. Every second is spent calculating the trajectory, trying to restore thrust, and searching for any chance of survival. So the next time you watch an airliner take off, remember, this titanic machine isn't just ascending into the sky. It's passing through an invisible field of tests where even the smallest feathered opponent can pose the ultimate test of strength.
The standard is the ability to digest a hit from a bird weighing up to 3.5 kilograms, your average goose or stork, without suffering fatal damage. But the main question is, can we just stop the bird from being invited to dinner in the first place? It turns out we can, and the solutions can be downright genius. One of the most elegant is the system of protective rollers on the air intake. It looks like a huge frame with freely rotating spools set in an angle. The working principle is laughably simple. The bird doesn't smash into a solid wall, but meets these spinning rollers. They act like a slide on a playground. The bird just slides off them to the side, remaining alive and unharmed, while the engine continues its work, barely noticing the visitor. Of course, there are more classical methods too, like special grills and protective mesh devices. But here, engineers have to work like jewelers. A mesh that's too strong disrupts the airflow, and the engine starts to starve, losing thrust. That's why each such device is calculated with millimeter precision, creating an invisible barrier that weakens the suction power just enough so a bird can't be pulled in, but without depriving the engine of its precious air.
You've probably seen the movie Sully with Tom Hanks. It's not Hollywood fiction, but a perfect illustration of what we're describing. In 2009, a U.S. Airways Airbus A320 struck a flock of Canadian geese shortly after takeoff. Both engines failed instantly. Captain Chesley Sully Sullenberger made the only right decision to ditch the aircraft in the Hudson River. All 155 people on board survived. This case is a textbook example of what a flock of large birds can do and what trained pilots are capable of. Interestingly, the primary threat isn't eagles or hawks, but strangely enough, seagulls. These fearless, opportunistic birds often circle airports looking for food and aren't the least bit afraid of the noisy giants. Small birds, like starlings, usually just burn up passing through the engine without causing critical damage. But the impact of a goose, swan, or pelican is a full-blown emergency requiring immediate and precise action from the crew. The statistics are reassuring. Severe incidents with complete engine failure due to birds are quite rare. Aviation authorities and airports are constantly waging war on birds, scaring them off with sounds, lasers, and trained birds of prey. Designers run rigorous tests, firing bird carcasses into engines using special cannons. But the fact remains, a large bird strike is one of the most serious threats in the sky. It can instantly turn the most complex mechanism into a pile of useless metal. Fortunately, thanks to extensive crew training and well-thought-out procedures, even such an extreme situation most often has a safe outcome. The key is the pilot's cool head and strict adherence to instructions that, without exaggeration, perform miracles.
Imagine an airport is a giant, perfectly manicured lawn.
Food, insects, rodents, garbage scraps, water, drainage ditches, puddles, and a complete absence of natural predators. For birds, this isn't an airport. It's an all-inclusive 5-star resort. And our job is to make this place as inhospitable as possible. How? Let's break it down. One of the primary methods is bioacoustics. Speakers set up around the perimeter of the runway aren't playing classical music. They're broadcasting in bird language. Distress calls of other birds, screeches of birds of prey, simulated gunshots. These are danger signals that trigger birds' instincts to flee. It's like walking into a cafe and hearing screams of fire and run. Your appetite would vanish instantly. But birds aren't stupid. They quickly catch on that the hawk screaming from the speaker is a bluff. That's when propane cannons come into play. These don't mimic anything. They simply create a deafening bang comparable to a gunshot. It's an aggressive sound that's impossible to get used to. Imagine a door slamming next to your ear every 10 minutes. Would you feel like hanging out? If sound doesn't work, it's time to attack their eyes. For this, they use rotating mirror balls and shiny reflective tapes. They create chaotic flashes and glares that disorient and scare the birds. It's like being stuck in a nightclub with a faulty strobe light. The fun ends quickly. But the real high-tech warfare happens in the air. Scarecrows have been replaced by predator drones. They don't just buzz. They can mimic the behavior of a flock of hawks, creating the illusion of a mortal threat. And the good old kites shaped like birds of prey work as Scarecrow 2.0, constantly hovering at the airfield's boundaries. The most natural and effective method is using birds of prey. Some airports have their own security team made up of trained falcons and hawks. Their mere presence is enough to make sparrows and pigeons look for another picnic spot. This is the Premier League of bird management. And when migration seasons hit, spring and fall, enhanced measures are deployed. Rapid response teams patrol the airfield with mobile units that combine sound and light. In extreme cases, pyrotechnic pistols are used. They don't harm the birds, but use a powerful blast of light and sound to scare them off. You might be thinking, so which method is the best? Just buy a bunch of hawks and call it a day. But the paradox is that no single method works perfectly and forever. Birds adapt. Today they're scared of the propane cannon. A month later, they're building a nest 3 meters away from it. That's why the key principle is a comprehensive approach. Sound disorients, light blinds, drones attack from the air, and hawks remind them of the natural threat. Together, they create an environment where birds are simply uncomfortable. It's like a security system. One lock is good, but 10 different locks are secure. This is how, step by step, aviation reduces risks, turning a bird's paradise resort into the most unfriendly spot on their flight map.
But what if a collision does happen? In the past, the pilot had to act almost blindly, relying on thrust and vibration sensor readings. The future offers a more elegant solution. Researchers in the UK are working on lightweight, wireless sensors, a kind of intelligent skin for the aircraft. These sensors determine the exact location, force of impact, and, most importantly, the engine's condition in real time. It's the equivalent of your car scanning itself after a minor accident and telling you, all is well, you can keep driving, I've already notified the repair shop to have the spare part ready for our arrival. For the pilot, this means the ability to make an informed decision, continue the flight, or perform an emergency landing, thereby saving time, fuel, and passengers' nerves. But what if the danger could be predicted hours in advance? The next frontier isn't just scaring birds away, but predicting their presence. Modern systems based on artificial intelligence analyze vast data sets. Seasonal migration routes, weather conditions, fog often drives birds toward airfields, and even local wildlife types. The result is dynamic risk maps. The airport control tower of the future will receive alerts like, warning, high probability of a goose flock arriving from the northeast in 2 hours.
recommend activating bioacoustic systems in Sector B. This transforms safety from a reactive process into a proactive one. Traditional methods are also evolving. Sound cannons and drones disguised as falcons are becoming part of a unified, automated network managed by the same AI. While one module scans the sky, another acts with targeted precision on the intruders. Simultaneously, a quiet revolution is underway in materials science. Scientists are developing composite materials and new alloys for fan blades that don't crack but absorb impact energy, like super-advanced armor. Imagine an engine receiving not a devastating blow, but rather a sort of elastic collision after which it remains operational. The future of aviation safety isn't about a single breakthrough, but the synergy of technologies. The all-seeing radar eye, the sensor-based skin, the future-predicting AI, and camouflage-like materials, together they create a multi-layered defense system. It works so seamlessly for the passenger that they will likely never know it exists. And that is the ultimate indicator of its success. While you're simply fastening your seatbelt, an entire army of robots and algorithms has already ensured your peaceful flight.